So thank you. Good afternoon. My name is Jirsa, and I'm here on behalf of Michal Maciszowski, who is the head of Center of Applied Physics and Advanced Detection Systems at Faculty of Nuclear Science and Physical Engineering. So our group is focused on development of radiation detectors, so for space as well, and our motivation for or requirements for the detectors is variable flux, measuring of linear energy transfer of the particles, and determine the character of the radiation. So determine whether it's electron, proton, ion, and so on. So they basically exist two types of pixel detectors. So one is hybrid, the other is monolithic. The hybrid is composed of two chips. Basically, one is the readout electronics, the integrated circuit. The other is the sensor part, which can be made from various materials. And these chips are then bonded together. The other technology, the monolithic detectors, are those where the sensor is integrated fully with the readout electronics on the same chips. So basically, you can see that on the other side. Yes. So our chips are based on silicon on insulator. So those are the monolithic pixel detectors. They have been made in 180 nanometer CMOS technology. And as you can see, the vertical cut of the chip. So the sensing part is in the handling wafer. And meanwhile, the readout electronics, which is responsible for the signal amplification, is separated by boron oxide box. So basically, you can have both integrated in one chip. So first chip which we have developed for measuring the radiation is X-chip04. It's a monolithic pixel detectors with 64 by 64 pixels. Each pixel is 60 micrometer pixel pitch, and the energy range, just this dynamic range, is between 1 to 10 kilo electrons. The chip itself is capable of photon counting or ADC mode. So basically, it counts each pixel number of photons which detect, or we can actually measure the energy of each incident particle. So on the bottom, you can see some pictures which have been taken by the chip. So here you can see some characteristic radiation, the X-ray image of wristwatch, and some particles, 150 MeV protons and xenon ions. The other chip, which is interesting, is SpacePix. The SpacePix chip has also 64 by 64 pixel matrix. And I will talk about it more detailed in next slides. So by default, the chip itself is radiation hard by the selected technology. But to make it even more radiation hard, we also triplicated the digital logic in the key parts. So there's the configuration register, row selector, and so these critical parts have been triplicated. So if a single event upset happens, the chips does not lost its configuration. It still remembers it. So here we can see the pixel architecture. So in the right, you can see the microphotograph of the chip. And if we take a look at one pixel, we can look here. In the center is the sensing diode. Then there is a sensing amplifier, peak detector, and hold circuit, which is connected by the column bus to ADC. The signal range of each pixel is between 2 to 80 kilo electrons. And you can see the transfer curve on the left. Another feature which has been implemented in the detector is the backside channel. So if really high energetic ion penetrates through the sensor, it saturates the pixels because it generates a lot of electron hole pairs. So you have big cluster and all of the pixels are saturated. Therefore, we have developed a backside channel which collects holes from all of the sensor, and then it has its own circuit for amplification and memory circuit, and then digitization. So the backside channel is its dynamic range is between 500 and kilo electrons to 30 mega electrons. With cooperation of ESC Aerospace, we have developed a 2SD instrument, which has been successfully launched to the space in the beginning of this year, in January. The 2SD system has two chips, two detectors, two instruments. First is the SXRM detector, and the other is SXM. These two detectors or instruments basically are in perpendicular. There's onboard computer, and everything is possible to integrate in any CubeSat, as you can see on the right. The SXRM is based on SpacePix chips. So there is 5 layers of SpacePix chip, as you can see here. Between each underneath each chip, there's absorber. So we can, when the particle flies through the telescope, we can in each layer we can measure the energy deposition, and we can get the energy of the incident particles. The other instrument is SXM. It's soft X-ray monitor, and it's based on X-Chip 03, which have been developed at CTU, and it basically measures, it's sensitive to photons, X-ray photons, from 2 to 18 keV. As has been talked about here several times, we are also collaborating in the mission LWC squared. We hope to be donating to this mission our detectors with collaboration of ESC and other partners, which have been discussed in the previous talk. So that's our goal for next time. So to conclude, we have developed and introduced 2 chips for radiation measurement. With collaboration with ESC, we have aerospace, we have developed and tested 2 instruments which have been successfully launched in ZLUSA-2 mission, and currently we are preparing for LWC squared. Also, we would like to, in upcoming years or year, we would like to focus also on developing radiation-hard electronics development. So that's it. Thank you for your attention. If you have any questions.
Thank you very much for your presentation.
Do you have some results from ZLUSA-2?
Yes, basically the campaign started a week ago. So we are not currently obtaining data. It's just actually these images are taken from the data, I think last week. So now we are acquiring the data, and we will. Yes, that's it. Now we are acquiring data, and we will process them.
Do you plan to? I'm not sure it works, but do you plan to use it also in CERN, for example, for LHC?
No, these chips
these are not enough radiation hard, or
they are radiation hard, but I think that the CERN is developing its own chips in-house. So I think they're not interested in these chips.
So thank you very much for your questions.
However, I can answer that we are also collaborating with CERN on developing their chips. So